right, so in your journal, go ahead and you're going to title this The Rest of Thermochemistry. It's a mystery. All right, so it's the rest of thermochemistry. Your test again is Wednesday. Okay, so I am going to kind of cut the chapter a little short, just kind of get you the basics that you needed to know, and then we're just gonna move on, so we can finish the year well. Okay, so what we're gonna start with on this page is you're gonna write math stuff, and we're just gonna write everything that you need to know that is mathy from this chapter. Okay, so the first thing that you guys started with was calorimetry, which we have spent so much time on that. So that one was the Q equals MCAT. And then in the lab, we learned that we can set negative MCAT equal to a positive MCAT, and you can usually solve for a missing specific heat or a final temperature or something like that. Okay? Couple things that we used in that was we said that degrees Celsius was okay to use. Okay? We also had to use 4.18 joules over gram degree Celsius, and that was the specific heat of water. Okay? So if you need more details, go to your packet and you can look up the minor details and all of that, okay, or the examples. You're going to give yourself a line, and we're going to keep going. Okay. Am I good with everybody? We're all good? Okay. So, the next one, and with you guys, I believe that was the one that I showed you guys like the wrong formula on Thursday. So we're just gonna start over on that one, and we're gonna go ahead and write Big Mama equation, okay? And just a reminder, the reason it's called Big Mama equation is because this general outline of this equation can be used with a lot of different variables in thermochemistry. So we call it the Big Mama equation because in the end it always is products minus reactants. Okay, and then so the way this one looked was you had delta H of your reaction. Please remember that RXN is reaction, by the way. Okay, was equal to, and then we made this fancy little E with a delta H of products minus another fancy E, delta H of reactants. Okay? Okay, so these little fancy E's, these guys are called sigmas. And I believe I went over with you guys what they were. Sum of, exactly. So the word sum tells us that we are adding things together. So, just for y'all's purposes, I am going to show you what was expected of you, what we were supposed to kind of write down on Thursday, and what you would do if you were an AP. But you guys are going to only be required to read two values off the graph and make sure you put them in the right spot in this equation, okay? So it's not going to be too bad for when you guys take your test. However, I do want you guys to see what it actually is. So I'm just going to take a second and just have you look at this. You don't have to copy it down. But what we're looking at here is you have a balanced equation, right? Does everybody see that? Okay, so we have a balanced equation, bunch of coefficients. Here is Big Mama. Here's the equation you guys just wrote down. Okay? What we do is we're going to look for all of our products. So we're talking about carbon dioxide and water. If you notice, we have to take into account their coefficients. So we would multiply their coefficient by a value that, I didn't put a picture on this, but you guys can kind of see it up here. See this big table? Do you see a bunch of little numbers? Yeah, all right. So there's like an entire thing full of all of these delta H values for all the compounds out there. And they tend to be your delta H formation, okay? So how much energy is needed to make them or break them apart, okay? That's what you're thinking. So that's where we would have gotten these numbers. And if they really wanted to ask you about it, they would give you them in a little table for you, okay? So once you have those in there, we keep these together, our products, and we're going to subtract all the information about our reactants. One thing to note here is that 0, anything when it's in its elemental form or by itself is always going to have a value of 0, just like your oxidation numbers if you kind of remember from redox. Okay? Then overall we end up getting this. Ignore the rest of this. This is an additional part to the question. But looking at this value, what does that negative sign tell me? It's a negative delta H. So what is that? Is that an endothermic or exothermic? It's exothermic, all right? So let's look at this reaction. What kind of reaction was this? Combustion, right? Do you guys see that? I was going to ask you, but all right. So what we have is we have our fuel, oxygen, and what are the products every single time? Carbon dioxide and water. I promise you this is still coming up on your finals. So if you don't know your types of reactions or you forgot them, you need to look at them, okay? They're over there on all the little posters. Okay, so that negative delta H definitely made sense because combustion we know releases heat. It makes fire, right? All right, so that's what Big Mama equation is actually used for. However, like I said, you guys are going to have this given to you. You're going to get a little graph that looks like that, right? Which we already know. What does this one mean? What kind of reaction is this? This is an exo, right? Okay. But what you're going to be given on this is you're going to be given two values. You're going to be given the value down here and a value up here. Those go into your little formula. So you're just going to have delta H reaction is H of your products minus H reactants, and that's all. Okay? So you got to know which one is the reactants and products. So up here, this guy up here, is this your reactants or your products? This is reactants. And then the one down here will always be products. So whoever comes first is reactants, whoever comes last is products. That's all you guys got to know. Okay? But I did want you guys to just say, that is how you actually are supposed to use it. Because that really is what it's used for. This is very simplified. Okay? All right, so that's Big Mama. You can go ahead and draw another line across. Kind of look up here when you're done so I know I can change. We're going to look over that bond energy next. All right, so the last thing I'm going to show you for today is going to be bond energy.
There's no tool going on in the Google Classroom.
Correct. Okay, so bond energy. So when you're doing bond energy, this is the one that I started going over with you guys on Thursday, was you're going to still have that delta H of a reaction. It's going to be equal to energy of bonds broken. That's an R, that's an N. All right. Minus energy of bonds formed. Okay. So I would say the trickiest part about this is making sure you draw your molecules. Okay, and knowing who gets formed and who gets broken. So give yourself like a little space and say formed and broken. We're going to talk about it real fast. Okay, so what we've got, for example, if I had the synthesis of water. Okay. Okay, the synthesis of water. We would look at this, and I would be giving you a table that looks like this, okay, or it might be a vertical table. But you can kind of see all your different pieces of information in here. So in this table, you can see that an HH bond has this much energy. Okay? A Cl-Cl bond has that much, an OH bond has that, and an OO has that, right? We're not really going to use a Cl. But looking at that information, now we just got to know where to put those numbers and how much to multiply them by. And I would say that is the hardest part, okay? So, just to kind of give you the things to look for, okay? You want to draw your molecules. So here we have H2. We have two H2s. So what I would do is I would draw two sets of H2s, okay? And then I have an O2. So I'm going to have O2. And then that's going to form two water molecules. So you have to be thinking logically here, okay? And which ones are going to get broken and which ones are going to get formed. So you got to decide reactants or products. Which ones get broken? The reactants, right? So obviously these guys have to get broken apart in order to reform those. So the formed are always going to be your products. And your broken are going to be your reactants. So the part that this kind of gives a few people issues, if you don't just sit there and think about it the way I just told you to, is that this one is now going to be reactants minus products, which is opposite of what Big Mama equation told you. But the reason we do it this way is because it makes sure that your ones getting formed are negative, because when you put things together, they have to release energy to squeeze in tighter. Okay? And when they're getting broken, they have to absorb energy, which is a positive value. So that's why it has to be in this order. Okay? Now, the only other thing to make sure you look at, okay, is you got to count up the number of bonds. So looking here, for this HH bond, we had 435 given to us down here. How many actual HH bonds are there? 2, right? There's one right here, there's one right here. So you would do 2 times that 435. Okay, plus, now we're going to look at the O2. How many O2 bonds are there? 1, so we would use this 498. Close your little brackets. That's the broken. That's what needs to get broken apart. It needs to absorb this much energy. Then it needs to release, okay, OH. How many OH bonds are there? There's not 2, there's 4, exactly. 1, 2, 3, 4. This is why you draw your molecules. Okay? So, and that's honestly it. So that's the math, and then tomorrow I will just review a few of the vocab things that I might have went really fast over, and then you guys are good to review and get ready for your test Wednesday.